Okay, last video. So in this video, I'm just going to show you how to reproduce all of the analyses in R. And one of the things that I want to do first is talk a little bit about the different package that we'll use to fit the generalized linear multilevel models. So I'm just going to open up a script. And so we have a new script here. I'm going to try to make this script a little smaller so you can see the script and the editor, and the console. And I have one thing that I want to do real quick is bring in the HSB file. This is the high school and beyond. This is the one that contains data that we've worked with in the past, where we're looking at mathematics achievement scores and SES. So there are two different packages. Well, one of them is NLME, and the other one is called LME4. So of course, if you haven't installed LME4 before, use the install.packages function. You can highlight and run that one. I'm not going to do this just because I have it installed already, but since many of you probably haven't had the LME4 package before, go ahead and use the install packages function, and you can download this one. Once you have it, you can load the packages in. So the library NLME, multi-library LME4. And the reason why I'm loading both of them in is because I just want to show you how to fit a model using NLME, and then I'll show you how to fit that same model using LME4. And so that way it'll become really clear how to translate the syntax from one package to the other. So let's fit a simple model using NLME. So let's say I do model.on1.lme. And usually we're predicting math achievement. So I have math achievement, I have an intercept, and I'll predict it with SES. And then let's say I have a random intercept and slope. This is from this model. Alright, so I get this output. I'm just going to copy and paste this into the syntax. You just have it right here. So let's do the same thing, and I'm going to do reproduce the results using LMER. And LMER is a function from the package LME4. So I'll do model.on1.lmer. And now I still have math achievement as a function of intercept plus slope. But here's the different part. So normally when we look at the NLME syntax, we write the random part as a separate part. So I would have a comma at the end of the fixed part, and then random as its own separate area. In LMER, this is all part of one thing. So it's going to be 1 plus SES, pipe, and then ID. So what this is saying is that, look, if you put this inside parens, that this is random effects, and both of these are by ID. So it's going to have a random effect for the intercepts, a random effect for the slope, and because they're both in parentheses together, there's also going to be a covariance between them. And then I have all of these here, and then by ID. So really it's the same as having the random part up here. The only difference is that it's in parens, right? So we're separating out the random part and having it in parens as one long statement. And then otherwise everything else is the same. So I'll say data is equal to data, NA action equals NA.exclude. I'll close the parens, I'll run the model. And then I get very similar estimates. Notice that something I want you to notice, right? So the most important part is that the fixed effects are virtually identical across these two. Right? These are the fixed effects from the NLME package. We see it's the 12.6650. We get the same numbers across NLME from MLAR. And the random effects are also very much the same, right? So we get these standard deviations here, and we see that they match the standard deviations down here, and the correlation is about the same with rounding. And LMER is also going to give us the variance estimates, so it's just going to square those standard deviations as part of the output. Right, so just to start out, one of the things that I wanted to do is to show you how to use the LMER function. And the reason why is because NLME package doesn't allow for generalized mixed effects models, so we have to use the LME4 package, which will allow for the generalized linear mixed effects models, or generalized multi-level models. All right, so now let's move on to a different data set. So I'll look at the depression data first. So fit the model to the depression data. So data CSV. And if I look at the first 6 rows of this data set, we have ID, we have age for individual I at time point t, we have their diagnosis, and we have their social support at age 14. So what I wanted to do is predict diagnosis with age, centered at age 14, and have both the intercept and the slope be predicted by social support at age 14. So one of the things that I'll have to do is create a centered version of age. So data $sign. I'm going to call this age CIT is equal to data $age IT minus 14. So now I have the centered version of age, which is centered at age 14. Now if I want to predict the intercept, I can just include the variable social support in the model. But if I want to predict the slope, I need to create an interaction between social support and the centered version of age. So let's do that. Data $, I'm going to call this int soc sup and age is equal to data $, age CIT times data $, soc sup 14. Oops. Underscore 14. There we go. Take a look at the top of the data, right? And so now I have this interaction term. So let's go ahead and fit the logistic MLM. So now I have model.o1.glmer. So it's the same as LMER because I have a G out front. So GLMER stands for Generalized Linear Mixed Effects Regression. So I'm going to do diagnosis for individual I at time point t as a function of an intercept plus a slope times age. And those two are random, so I'm going to do 1 plus age c it. And then I have an effect for predicting the intercept, and an effect for predicting the slope. Oh, sorry, I need to do one other one. I have to include this family is equal to binomial because this part of the code right here will indicate to the GLMFR function that diagnosis IT is binary. So it's going to say that it's going to take on values of zeros or ones, which is why I got an error. Because without the family equals binomial, the GLMER will assume that this is a continuous outcome, and if this is a continuous outcome, then I should just use the LMER function. And so it's asking me to use the family equals that one, so I'll run this. I can look at the summary. Right, and these are the effects that I received from R. And so I have the effect of the intercept, right? So the log odds of obtaining depression at age 14 for someone who has average social support. So remember that social support was mean-centered prior to reading in the data. So this is for average social support. This is the rate of change in the log of odds across adolescence. For each 1 unit increase in age, we expect the log odds to increase by 0.16, right? And that's for an individual who has average social support. Okay, at age 14, higher social support leads to lower log odds of getting depression, diagnosed with depression. And the slope, right, for the relation between age and depression, it doesn't really have much of an effect or much of a relation with social support. Okay, so we can reproduce it this way. As you can probably see, the modeling procedure is very similar to what we've seen before. We just use GLMER. We have a little bit of a different statement for the random effects, right? So we just include that in the model statement itself, and we include the random effects in parentheses, but otherwise everything stays the same. Remember that we have to include families equal to binomial, right? And this is for dichotomous outcome variables. And if you're interested in other types of variables like Poisson, there's a different one. I think it's family is equal to Poisson, but I could be wrong. You just have to look it up real quick. But then everything else, you run the whole model, you look at the summary, everything stays the same. Okay, so we can move on to the second example. I'm just going to save the code real quick. I have clicked the wrong button. Let's see if this cancels out. Bummer. I think I have to force quit R real quick. Let's see if it's same. Ah, okay, that's great. Okay. Let's do the second example. Data is equal to .csv. Oh, and I haven't, oh no, the admission data. Yeah. Admission to graduate school. And so we have admission to graduate school for individual I and college G, right, which is taking out a value of 0, 1. We have SES, and we have schools and students within those schools. And so in this example, I'm going to open the LME4 package again because I had to close out R. I needed to reopen it. I have model.o1.glmer. So in this one we had admission for individual I and college G as an intercept plus a slope for SESIG. And I think one thing that I needed to do was to create averages of SESIG. So let's do that real quick. So let's use the ddply function to obtain average SES for each of the schools. And so I'm going to put the library function up here. Open multiplier package, and then I have means data equals ddply. And I have dot data is equal to data dot variables is equal to school ID. And then I have to summarize, and then we'll call this mean SES. SESIG, sorry. And so I have each of these means. Okay, so I'm going to use data merged is equal to merge y is equal to means data. Y is equal to means data. Oh, it should be, sorry, I'm going to bring this down so it's a little easier to see. By should be school ID, not just ID. Okay. And so now I have SES, mean SES. I think I also need to make a centered version of SES. What we'll do is we'll say data merged SES centered within school or centered within college. It's kind of fun that the acronym works out that way. Is equal to data merged dollar sign SES IG minus data merged mean SES. Okay, so now we can fit the model. I'm going to create this to. I have random effects for both the intercept and slope. And this one, in this case, I only predicted the intercept, so I'm just going to include me in SES here. Equals data merged. Right. School ID again. And we get the effects. Okay, so this is a pretty easy, straightforward way to produce mixed generalized linear mixed effects models in R. I might go over Poisson at some point. We'll see how much time we have on the class, because I think I'd rather cover missing data if I can. We'll see how it goes. But yeah, so hopefully this is relatively straightforward. We should be able to see that it's just a simple extension of multilevel models, and it's also just a simple extension of logistic regression. Right? So from logistic regression to logistic multilevel modeling, we're incorporating random effects. Right? So we have random intercepts and slopes, and we can predict those random intercepts and slopes with the variables. And again, it's a kind of a simple extension from multilevel modeling in the sense that now we're predicting the log of the odds as the outcome variable. And if we wanted to exponentiate these, we can. Of course, yeah, I should show this. If you want to exponentiate really easily, if you do exp to the negative, we'll just do 0.56. Right, this is going to give us the 1.75. So this is the same as e to the power of 0.56. So by using the exp function, we can do this really quickly in R. Otherwise, everything stays the same. Okay, thanks for watching. Hope you enjoyed the videos, and I hope you have a good Thanksgiving break, and we'll talk soon.